Hello, everyone. B. Alfred Ostrowski here, and in this recording, in a continuation of discussions on theory of computation, lecture 7, I'm going to be discussing the elimination of left recursion. So before I do that, let me explain exactly what left recursion is and why we want to get rid of it, right? So let me write a simple language, rule definition, and in the format as we've been utilizing up to this point of context-free grammar. And I can define a simple language of the following format over the language of simply A's and B's, right? It's my language, it's my letters, and that's my complete grammar here, right? So just as usual, what's in my language? What words exist out of this infinite combination of A's and B's? I would have a B, obviously. I can go with A to a B, right? But I can go to any number of A's, in this case, after the B, right? Because I would generate the A's first, and then the A would go to B. So I have a BA, I have a BAA, BAAA, so on and so forth. And what would correspondingly not be in my language be any combination of AB or ABA or AAB, so on and so forth. Let's prove it to ourselves, right? Let's exercise the derivations of this one rule grammar. To get some of the word examples, let's do BAA. How would I go through my derivations here? I would go A would go to AA through this rule. And this A, this non-terminal A, could be, once again, be replaced with AAA. See how this is going, right? We are going through a recursive process. It could be an infinite number of A's before that B. And that A could go to a B, and that would give me the appropriate demonstration of that word example, how that exists within my language. And how did I get there, right? I recursed with that non-terminal, and I could recurse any number of times. And I'm recursing on the left-hand side, right? And this is a comparison to what? I can have recursion on both sides. I could have a rule, or I could have an AA, something of that nature. That would be both left and right recursion, or I could have, in this case, an AA, B, and on very quick observation, you may be saying to yourself, well, looks like the same language to me, but it isn't, right? Because if I do go through the derivations, if I go A to AA, for example, and then I apply the B, I would end up with an AB, which would be not in, that makes the designation between this language and that language. And this language definition that I'm applying here, that's recursing to the right. Okay, so what I want to do is be able to express a grammar with this kind of attributes into a format of this, but obviously I just can't simply just change that over to the right, because that would give me a different language, right? So I need to understand a quick means of manipulation. And back to my original question, why are we doing this in the first place? Why don't I just keep both of them? The more you work with the derivation of these grammars, and the grammars will become increasingly complicated and sophisticated. That's where we have the designation of linear as opposed to what? Those linear grammars to nonlinear. And context-free grammars, where I am not looking at context to specific context definitions, context-sensitive grammars, and yet even further going into unrestricted grammars, give me the functional equivalent of a Turing machine capability, and a Turing compatibility. Okay, so we talk about Turing compatible languages, right? That it can do anything that any popular programming language can accomplish. So we want to support these normal forms, Chomsky normal form, Greibeck normal form. Most importantly, in this case, we are setting up the premise, warming up, if you will, to support the derivation of the Greibeck normal form through the elimination of left recursion. The reason is consistency, simplicity, right? I want to make my grammars more consistent, more simplistic, to support real-world implementation that can exist in the compiler design, it can exist in natural language processing, and it does. So there's a lot of practical applications. This isn't just a theoretical exercise, right? This is a means of standardizing these grammar representations, which hopefully at this point you already have an appreciation that it could become extremely powerful, right? So we want to make sure that we're getting a level of consistency and perhaps most importantly, efficiency. And that's why we have these normal forms. And in the cognitive theory computation, it really sets up a strong premise and foundation for implementation of compiler design. That takes you from your theoretical aspects to a more practical application where compiler design would obviously be a definitive practical application. So that's what left recursion is. It's how it works. And most importantly, why we're interested in learning about it, and in some cases restricting or eliminating it, right? So let's go through some examples of how do we get from point A to point B here, going from a left to right recursive example. So let me just clear my slate here. And let's work through some simple examples. So just like everything else, this is a function of practice. And the more you go through it, the more comfortable you have, and it's not too difficult once you get the hang of it. So let's just go through a brief example, kind of start off with our same example here. And this generates English language description of this language is 1B with any number of A's following that, right? Because I know to terminate this, I have to go to the B, and the B will assign to an A, which is the non-terminal A is assigned before all the terminal A's, which I can leverage my recursion to generate that infinite number. So how would I go through that representation? I'm going to add a new rule, okay? And the new rule is going to be in a right recursive format. So, and I do that by obviously not considering this in my redefinition of A, but I'm going to consider not just this terminal, but any terminal characters that may exist in that rule. In this case, I only have one. I've simplified it, for example, purpose. Okay, so let me rewrite A and go through what we did, and most importantly, why we did that. So I rewrote A as B, and I created a new non-terminal Z. And this, if I take E, A to B, that takes that first instance, and it's just the same. It existed the same all the way before, right? I'm only really interested in modifying this. So this will carry over to the same. In this case, and we knew just through prior examples, I would have B, and it's just as I have discussed just a minute ago. In the English description, it's a B followed by any number 0 more A's, right? So in this case, I'm going to have a B, and Z is going to define it in a right recursive fashion, that definition of any number of A's. And I know that now I don't have to worry about terminal B in this second definition. I can write it in right recursive format and get that same level of functionality. The downside of this, right, obviously I have to go from one rule to two rules. but this is giving me a consistency to bring it all to that consistent form, which I'm going to be relying in Greibeck normal form. But again, I prefer to break this down and get that level of comfort with the elimination of left recursion, and then we can jump right into Greibeck normal form and go through the examples in a lot more efficient manner. Okay, breaking that problem down. So let me look at this rule, just look at it independently and just look at the English description. What is this giving me? Unlike the initial A going to non-terminal AA, terminal A, and or B, I have only A's. So everything that exists in this language is all these A's that would exist. So if I consider this as a separate language, I can say Z go to A. That would be one word that exists in that language. And I can have Z go to AZ and replace that Z with another AZ, right? And so on and so forth. In this case, I can derive 4 A's. It could be any number of A's, right? Once you do it a few times, you have the comfort level. So that's what Z is buying us. Okay, so from an English perspective, I'm saying take in this redefinition, right recursive format, I'm saying B and any number of A's. So that gives me back to the original definition here. So this is the complete elimination for a very simplified example of left going to right recursion. Okay, it's giving me the same exact representation, the B followed by any number of A's. And the means of verifying this is also always look at what is my language, whether in example-based or English as description or in both, right? Just have that comfort level and then taking your final product and doing the check against that, those given examples. So this can become a little more error prone when you're looking at larger descriptions, but the same principles apply. And the same logic that's applied in this example applies to any example, okay? The issue with Greibeck normal form is the fact that when your productions are, your heuristics get very lengthy between the elimination of left recursion and substitution, there can be a little bit of confusion just because it becomes a little bit more cumbersome. So for that reason, just in the same manner of some of the more sophisticated representations such as Turing machines, it's best to just work with smaller examples, knowing with the fact that I can expand it to any level of complexity if it's so needed. So let me do another example here. That's a little more longer example. Let me look at another rule here. And this is over the language A's and B's. And I have 2 left recursions and 2 terminals. So once again, these are going to be the same. I'm going to rewrite A to eliminate that left recursion. I can jump straight ahead to the process. I'm sure that you already have a comfort level of how these rules are going to be generated, right? So I can rewrite A to eliminate that left recursion. I'm going to put B and C. I'm going to keep that just the same. But I'm also going to put, and I could have put that later on, right? I'm also going to create a new non-terminal B of Z and C of, again, non-terminal Z, right? It's capital letter. So here I'm going to write that non-terminal, and how's that going to be expressed? Well, once again, we can look in terms of English description, and I can define Z as, and it becomes a little bit more intimidating again, just due to the sheer size. I can say AZ, BZ, A, and B. All right. So how did I get that, right? Here I am, when I had non-terminal A and non-terminal B, and what I don't have here is in Z, I don't have the inclusion of C, right? So B and C being the end, but interestingly, I can end, I don't have to, this looks a little bit odd that I have B here as terminals in both the Z statement as well as A. But if we look at specifically what I'm explaining, defining here, is that I have, just as I originally had here, this is really defining any number of A's, infinite number of A's. This is defining it from a right perspective. And here I have an infinite number of B's, right? And this is accomplishing the same fact. However, it's accomplishing it from a right recursion, but I'm not including C. B is a wash because I could end it with a B, but it's going to be a language mixed with A's and B's, and I could have a B at the end in a similar fashion. But you can obviously work that out with specific examples to see how that would work. So here I have, and again, I have an A and a B. Why? Because I may have a single A and I may have a single B. I don't even need to recurse, right? I may have, in this case, what's in my language here? I would have, and maybe I should have done this first place, but I could have BA, right? I could have an AA, and then that A go to a B. I can have a BA in my language, similar nature. I can have a CA in my language using those rules. And I can see here, I can have a single A here or B, and I can implement that in my language here with B going to Z, Z going to single A or B, or any number of A's or B's or combination of which afterward. And I can work through any number of examples. So what's the overall heuristics that I'm looking at? When I rewrite A, what are our definitions? And this is the answer, right? This is elimination of the left recursion. If I look at my answers, I want to get eliminate the non-terminal on the left-hand side. And I did that here. So I need to replace these two productions. I keep these, and then I replace these with Z, because I know when I look at what is in my language, it has to begin with a B or a C. And if I want to, again, put it more of an English description as to what is in the language, is a B with any number A's or B's, okay? And that's what this was buying for me in the first place. And the C in the same fashion, right? Any number of A's or B's. And that is what's being expressed. And I can see here, if I assume, well, my English description was any number of Z is giving me what from an English description? It's giving me this, right? It's giving me that any number of A's or B's, and we can look at that and it makes sense, right? And once again, how did I get there? I eliminated all the left recursive, and I made a mental note that I'm going to turn them into right recursion. And I'm also going to take the instance that I may not recurse at all, right? I may just go directly to the non-terminal. I need to represent that directly into Z, because unlike here, I didn't have to go there in the first place, right? So the fact that I'm going there, relying on that, and that's condition is represented here in the non-terminal B and C's. B and C, B and C by themselves exist in that language, right? And again, I can consider what's not in the language. That would include, let's say, A and B, A and C, and so forth, and plug that in. So those are the heuristics. That's how I drive. And this is, if you look at this and compare this, just the last example I did, you can see the effective comparison between the approaches and their similarities. And most importantly, if I match this to the English description, I can understand that logic. And most importantly, understand why I did it and not be confused by it, right? Then I can know, well, I'm going to replace this with this and perform my substitutions appropriately, generate that extra rule in this case, and consistently apply that across the board. So this is our tool in our toolkit to immediately resolve the conversion to graphic normal form, which is going to be following this presentation. But this is a nice way just to break that down and individually look at the elimination of left recursion. And then we're going to be good to go with the graphic normal form, as well as any type of activity of normalizing our grammar, simplifying it, and building it into a standard approach, most importantly, to support efficiency in implementation if you need to support any type of practical representation, such as compiler design, that's going to represent a lot more efficient base representation. So thanks for listening. Hope this helps. If you got any questions, feel free to contact me. Take care.